Okay, this video is going to get us thinking about how we might look at data points from experiments using reversal designs and the like in ways that help us make conclusions from visually analyzing what we see, no statistics needed. So visual analysis of data is also used in other areas of psychology like psychophysics and even by our colleagues in physics itself. I know psychology students are used to thinking of statistics as kind of a magic tool to answer questions, but statistics is just one tool and has its own limitations, and a lot of science actually doesn't use statistics and doesn't need to. With enough data in clear enough patterns coming from studies with appropriate design and control, we don't necessarily need statistics to make conclusions. So let's talk about the visual analysis of data. Well, books and books have been written about the topic by those specializing in psychometrics and measurement and things like that. We're going to start pretty simple and just consider 4 things that we want to look for when visually analyzing data to see if a real and meaningful change has occurred. The 4 things we'll look at in turn are summarized on this chart we'll start with. So first, we will look at the overall level of the behavior during each phase of the reversal design, and whether the overall level is different when we reverse between those phases. So that's level. We'll also need to take into account the trends within each phase. In other words, the direction, whether the behavior was going up or going down within a given phase. Additionally, we're going to want to look at immediacy, which is how quick or extreme the change is when we flip the switch in reverse conditions. And finally, it'll be necessary to consider the level of variability within each phase and compare that to the variability or change when we compare between the different phases to see if a change after treatment is bigger than the random noise and variation that we already expect. But let's start with examining the level of the behavior on the upper left here. So in general, a consistent change in the level of a behavior at least suggests that the treatment may be having an effect. And perhaps more importantly, this is a good way to feel out the size of the effect. So if we go from a high level of the behavior to a low level of the behavior, that's going to suggest a bigger effect size in addition to providing more clear evidence of a real change. Whereas going from a high level to just a moderately high level of the behavior might not be enough of a difference to be clearly real, nor a change big enough to be interesting. Now, when we're talking about level, you can often eyeball it, but to be more formal, you might calculate the average of the data points within a given phase. So kind of draw a horizontal line through whatever the average number is of these 5 data points. Maybe it's like 94. So 94 would be the average level for this left phase. And this phase here at the moderate level, maybe that average is around 51 or something like that. So we saw in the previous slide, in the bottom right here, we saw in the previous slide where they drew these little horizontal lines at the average level within each phase. That's what we're talking about when we talk about level. That said, though, drawing a horizontal line to describe the average level within each phase, it does leave out what might be some pretty important information. Like if the behavior keeps consistently going up or consistently going down during that phase. In other words, if there's not just some random variation within the phase, but a movement in a particular direction. So we also need to look for what we'll call the trend in each phase. By trend, we just mean the overall slope of the behavior during that stage or during that phase of the experiment. So for example, the behavior here on the left graph, it's clearly rising over time, even before we introduce any sort of treatment. Notice also how much more clear it is when we graph it out visually compared to when we just look at a long string of numbers, right? Both contain the same information, but patterns can often be easier to pick up when we make things visual. So if the behavior is going up during a phase, we would say it's an increasing trend. If it's going down, we'd say it's a decreasing trend. And of course, sometimes it's relatively flat, so there's no trend in either direction. The reason this is important to pay attention to is imagine there's an upward trend in all the baseline stages, right? The A stages of our AB, AB, AB reversal. And maybe there's a downward trend during all of our treatment stages, the Bs in all of our AB, AB design, right? That would provide additional evidence that the treatment is changing things and specifically even changing the trend, changing the direction of the behavior over time. Here's another example from an old study using an A-B-A-B design. The behavior they were measuring was how many assignments a kid with special need was completing. So more behavior here would be better, right? You want them to complete assignments. And the treatment phase, the B phases, had an intervention where they used tokens as reinforcement. The actual data here is the circles, the filled in circles connected with solid lines. That's what happened during the experiment. But notice on the graph, they also they filled in some dashed lines. Those are projecting forward the trend from each of the previous conditions, each of the previous phases. In other words, you can think of it like fitting a least squares regression line to the prior phase's data to get a line with a particular slope. That's the trend, meaning like a line of best fit between these data points, whatever its slope is, that's what they've drawn here just to kind of highlight. That's the trend we were seeing before we switched. And if you compare the trend that was happening in the prior phase, right, what you would expect if the treatment didn't do anything, you can see here that the real data is very different. In the first baseline phase here, the behavior was flat and not increasing. So the fact that when we go into the treatment phase, it shows a new increasing trend, that tells us the trend changed in that phase. Something has changed. The intervention likely had an effect. Likewise, in the next baseline phase, you can see that the trend is downward, fewer assignments getting completed. But as soon as we turn the token intervention back on at the end, the directionality changes again. The trend changes. Combined with the change in level that we're also seeing, the change in trend is sort of additional visual evidence that the treatment might be doing something. Last example for trend, we're measuring here tantrums. So in the y-axis, you can see number of tantrums in a toddler. Here, the intervention seems to be changing the trend, right? In the baseline phases, tantrums trend upward over time, but in the treatment phases, tantrums are trending downward over time. Now, obviously, if we did even more reversals beyond this first month, we could get even more confidence in the effect, more confidence that it's real, right? But often, even if this isn't 100% certainty, a month-long study like this might be enough evidence in this one case for these parents to decide, yeah, we'll adopt that intervention. We'll do things different. Oh my God, it's so much better with a lower number of tantrums. All right, that's the change in level and change in trend that we've talked about. What else do we look at when visually analyzing data for single subject designs? There's also immediacy as another important element. That just means whether switching conditions quickly and immediately changes the behavior, or whether it takes a few data points, a few days, a few sessions before it starts to move up or down to the new level. So in the example we see here, you can see on the y-axis to the left that we're graphing someone's non-compliance behaviors, sort of what percent of the observed time intervals they were non-compliant. In the baseline, it was pretty high, almost constant non-compliance by this person. But look at the very first session when we start the treatment. So here's the treatment. Here's the data for the very first session. It seems like instantly the non-compliance is much lower and pretty consistently stays lower during that phase. Not even on the most non-compliant of these treatment days, so the worst, the most non-compliant of the treatment days, are we anywhere near even the lowest non-compliance of the baseline days. Right? We've jumped pretty significantly, and we jumped instantly. So that's immediacy. It didn't take 3 or 4 sessions for the treatment to start working. It was immediate. When the treatment is removed and we reverse back to baseline, it immediately jumps back up. And likewise, turning on the treatment again sort of instantly gets results on that next session. So we would say this data, if we see something like this, we would say it shows a lot of immediacy, or it has a high level of immediacy. But compare that to this data instead, right? This is the same graph we saw earlier for an intervention using tokens to reinforce something positive. In this case, we don't have much immediacy. There's much less immediacy, much less of a quick, big jump compared to what we saw in the last slide. That doesn't mean the treatment doesn't work, right? Some things just take time or cause incremental improvements. But when we do have lots of immediacy, that can strengthen our evidence for causation. It can make us more confident the treatment is what's causing changes. So more immediacy is better for making these conclusions. Finally, the last element that's essential to pay attention to in visual analysis is variability, meaning how much variation there is within a given phase of the experiment. So less variability just means a behavior is more stable. It's more predictable. Look at Jane's performance here at the top. She's almost always right. She's almost always, around 80% correct, like right around 80%. So it's very consistent. That's what we mean by low variability, is very consistent. But compare that to Matt at the bottom here. He has tons of variability in his performance. He's jumping from near perfect scores sometimes to pretty abysmal performance other days. The difference in variability here, that just means that it'll be easier to see whether a treatment affects Jane than it will be to see whether a treatment affects Matt. Matt's got so much variety and kind of randomness and noise to his data already that even if we institute an intervention and he got a few high scores, it might be harder to tell whether it worked because sometimes he already has high scores as part of his highly variable existing performance. Look at this graph, another example here of problem behaviors over 11 days. Let's say we start doing the intervention on day 6. It's pretty hard here from this data to tell if the intervention worked because this person already had a pretty big range of good days and bad days during the baseline. So that existing variability, it can mask our treatment's improvement, if there is any, and make it harder to spot. That doesn't mean things are hopeless for highly variable behaviors. It means the more variable the data, the more variable those existing behaviors already are, the more data points are going to be needed to demonstrate a consistent pattern of change. So if we want to be confident in an effect, we might have to take 50 or 100 days of data rather than the 11 you see here. Not to mention we'd obviously also want to do more reversals than what you see here, which is, no reversals. Okay, here's 2 ways some data might go in an A-B study. Look at the bottom graph first. In the bottom half, imagine the treatment does nothing at all and the entire data set is just part of that child's normal variability. Maybe the kid just goes up and down from 5 to 75 throughout the year, and we just happen to catch some of that natural variation. If so, our treatment didn't actually cause these changes we're seeing. We just don't know from a pattern like that. But that alternative explanation, it's much less likely for the data in the top graph, right? Yeah, this kid had some variability during baseline, and indeed, some variability within each condition. But notice that the variability within conditions is smaller than the variation or the difference between conditions. In other words, the treatment data doesn't really overlap at all with any of the baseline data. In the treatment here, we're getting numbers that just never happened during baseline, and vice versa. They're outside the normal variability of those conditions. That's an important thing to note. That gives us some evidence that we're talking about a real difference here. So, okay, let's try applying these ideas to some new data. Here's a study done on some rabbits to see the effect of feeding on the pH of their urine. If you were doing a visual analysis of this data, how would you describe the 4 elements that we've talked about, the 4 elements we look for? Take a moment to pause the video and think about each of these 4 elements. Okay, first off, the immediacy is pretty obvious here. We'd say there's a high immediacy, a lot of immediacy, because the change always happens right on the first day that the feeding situation has changed. Okay, what about the change in level? Again, I'd say this is pretty obvious here, a pretty extreme change in the average level during each of the phases. We're talking quite high versus quite low, right? Not a subtle little difference of just a little bit. Okay, what about variability? Well, overall here, I'd say there's not a ton of variability, though certainly there's more in the 3rd and 4th phases. There's some, but importantly, the variability, even in those 2 conditions, even in the 3rd and 4th condition, the variability within those conditions is not so extreme as to be anywhere near the change in level that we're seeing. We're getting a much bigger change when we switch between conditions than the variability we're seeing within conditions. By the way, that is literally how statistical methods like a t-test and an ANOVA work. They just compare the amount of variation between conditions to the amount of variation that's already existing within conditions to conclude whether it's a real difference or not. Okay, finally, what about the trends? Here, I'd say like nothing really stands out as hugely obvious, at least to my eyes here. The first phase definitely looks pretty flat, but it's a little less clear if we'd say the second phase is maybe trending a little bit downward or pretty flat, whether the third phase is trending upward or pretty flat, but certainly there's no big obvious pattern here that would undermine the idea that grass versus fasting causes a change in the pH of the urine. So there we are. That's the basic idea of visual analysis of data. These are kind of the four main things we look at. There are, if you're curious, there are some statistics you can run to formalize or automate this process. But frankly, in general, we hope to collect enough data and see obvious enough patterns that the stats literally aren't needed. Just like physicists in many experiments don't need statistics to see a clear pattern of differences when they manipulate something in their experiment. Now, before I end this video and conclude our introductory warm-up topics, let's do one last practice with visual analysis. Let's compare the result of two experiments here, two ways that our data might turn out when we do an ABA design. If I ask you to compare these, the top version versus the bottom version, which one has more immediacy of these two? What about which one has more of a change in level? And what about variability? Specifically, if we compare how much variability there is within phases versus the variability or difference between different phases, which one has more? And what about the trend information? Which one gives you more clear trend evidence that the treatment causes changes? I'll leave it to you to answer those.